Alright, probability. Let's start off with some definitions. Probability itself. Well, probability is simply the chance of something happening. Experimental probability, also known as relative frequency, is when you work out the probability based upon data that you have collected. So, for instance, you toss 5 coins and they land heads, heads, tail, tail, heads. You'd say the experimental probability of tossing a head is 3/5. Now, theoretical probability would be, of course, 1/2. The number of times you repeat the event, as that approaches infinity, in other words, the more times you do it, then experimental probability should approach the theoretical probability. A sample space, all the possible outcomes. And event space is just the number of ways a particular event can occur. Equally likely events. They are events that have an equal chance of happening. Mutually exclusive events means only one of those events can occur at any one time. So, example, a coin could either be a head or a tail, but it can't be both at the same time. So they're mutually exclusive events. Non-mutually exclusive events then means that the outcomes could happen at the same time. So a number could be both even and a multiple of 3. 6, for instance. Some notation. So P and then E in parentheses, the probability of whatever E is happening. And then when we put a bar over the top over E, we get the complementary event, so the probability of it not happening. So let's recap the basic ideas of probability. Now, you'll recall that a probability of something must lie between 0 and 1. I mean, yes, theoretically it could be 0 and it could be 1, but usually it's going to lie between 0 and 1. If it did happen to equal 0, then we're saying, well, the event is impossible, could never happen. And if it was at the other extreme, we'd call that a certain event. It has to happen. So if all the events are equally likely, so the sample space, every possibility that goes in that sample space would be equal, the probability of happening, so we'd say it's uniform. Theoretically, there's the formula for finding the probability of something. Now, it's not a formula we usually write down, because probability is a very logical thing, and we tend to just write the probability down. But the actual formula is that probability of E is equal to, and it looks like I'm saying the absolute value. What it means is the number of times E occurs over the total number of possibilities. So the actual size of the sample space, if you like. So the first one, size of the event space, all the possible events that could happen. And size of the sample space, the total picture of what we're looking at. This is what we call the complementary event idea. Sometimes it's easier to work out the probability of something not happening rather than the probability of something happening. Well, because all the probabilities have to add up to be 1, then the probability of something not happening must be 1 minus the probability of something happening. So we need different ways of how can we list the sample space so we know what all the possibilities are. Different ways. We could simply create a list. We just write down every possibility and hopefully we don't miss any. And that quite possibly is the simplest way of coming up with a sample space. Just list everything that could happen. Quite an old example now from the 2004 HSC. So we've got this game, it involves rolling 2 dice, but our dice are a little bit unusual. Instead of being numbered 1 to 6, they're numbered 0 to 5. And the score for each turn is calculated by multiplying the 2 numbers that appear uppermost. So I'll just write out every possibility, but in red then I've also written down the result. So if they both turn up 0, we get 0, and if it was to turn up 1 was a 3, the other was 2, we get 6, and so on. So I now know what every possibility is. So part I of the question said, well, what's the probability of scoring 0 in the first go? Well, it's just a matter of counting now. I mean, it's, oh, look, oh yeah, there's one. Oh, look, another one. Oh, excellent. So 11 out of the 36. As I say, it's probably the simplest way of working out a probability problem. Second one, what's the probability of scoring 16 or more? Oh, I'm looking for numbers that are 16 or more. Well, there's 4 of them. So 4 in 36, which of course is a 1 in 9 chance of happening. Another way of coming up with a sample space is what we call a dot diagram. So a pair of dice are thrown. I'm using that example again, but this time I'm talking about regular dice, 1 to 6. What's the probability that they total 3, they total 7? Well, a dot diagram is very similar to just writing out the sample space, but instead of physically writing it all down, I create a grid and put dots at every possibility. So then when I want to work out the total of 3, instead of in the last one where I circled the actual combination, I'll just circle the dot that represents. So total 3, I've got 2 dots there that would represent 3, a 2 and a 1, and a 1 and a 2. It's a very similar idea. Total 7, which is actually the most common one you could have, hence explaining why the opposite sides of the dice total 7. 6 on 36, which is 1 in 6 chance. At least 3. Well, rather than working out all of those, this is where I'll use the complementary event idea, because it's probably going to be quicker to find out how many just total 1 or 2. So how many total 1 or 2? None of them total 1. It would be impossible to get a 1. The one I've circled there is 1 and 1, which is 2. Impossible to get 1. So there's only one possibility. So the one I want, it would be 1 minus that, because I'm using the complementary event idea. 35 and 36. Tree diagrams. Tree diagrams. So in a raffle, 30 tickets are sold. There are 2 prizes. Probability that if you go and buy 5 tickets, that you win exactly 1 prize. So a tree diagram, because we branch out in the possibilities. So I could either win or lose. Probability of winning, well, I've got 5 tickets, so 5 out of 30. So probability of losing, 25 out of 30. And then I branch again. Now my first branch there is assuming I won on the first ticket. So there's only 29 tickets left. They're not, I don't know about any raffle that puts the ticket back in, so you get another chance with the same ticket. So there's now only 29 tickets. I've now only got 4 in there because my first one won. So it's 4 out of 29 and 25 out of 29. But if I assume I lost on the first go, then I'd have 5 on 29, 24 and 29. To work out the overall probability, we multiply along the branches. So there's the possibilities: win, 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 loss, loss, win, and loss, loss. Multiply along the branches, and we come up with the probability of each of those things happening. Now, they want exactly 1 prize. So that's the 2 middle ones. So a win-loss or a loss and a win. So 25 on 87, that adds up to me. So using a tree diagram. What's the probability of winning at least 1 prize? Well, again, I'll use the complementary event idea. That word, at least, or at most, those sort of words, that's when you're thinking, maybe the complementary event's easier to use. So what is the complementary event to winning at least 1 prize? Well, the other thing that could happen would be I win no prizes at all. So 1 minus no prizes. Have a look at my tree diagram. There it is, 20 on 29. So 1 minus that is 9 on 29. All right, so as I say, bit of a recap of our basic probability ideas.